Okay, I think we should start. And the first talk is on bulk acoustic wave devices for high-frequency gravitational wave antennas. And we have Tommaso from INFN and the University of Milano. And please go ahead.
Okay, thank you, Mike. So let me introduce myself. I'm a particle physicist, so I'm new to the field, and I'm actually would like to introduce myself as a student of Mike, because I'm collaborating with him in understanding these devices. So I will cover briefly the potential sources for gravitational waves in high frequencies, because when you think into a detector, you have to see which signal it has to look at, and then I describe the detection approach and the status, particularly what we are doing in Milan to supplement what has been done by Mike and his collaborators at the University of Australia. So, well, this is taken from your white paper, and as you see here, the bulk acoustic waves that I will describe shortly have some sensitivity to the coherent sources. Here, the line here is for a reference amplitude from Milky Way distance, and so they standard devices. So those that have been developed in several years for precision clock applications in several fields are responses over a wide range of frequencies between, say, 1 megahertz to 1 gigahertz. Sensitivity is not flat, but it's okay. They cover that range, and it's possible to customize them also to cover other frequencies, as I will comment. So let me first discuss briefly the sources, the coherent sources, where there is some sensitivity. For the incoherent one, those are much below the expected sensitivity. So this sketch you have seen already. It was introduced by Andrew, and the sources that we could target are gravitational waves from axions. So this model that was described in before, that requires sensitivity in the let's say 100 kilohertz range, and that is marginal for the established bulk acoustic waves, but it's coverable with some customized bows that I will explain. And the other one are in spirals from primary black holes that can contribute up to about 10% of the dark matter planetary masses, which would give an emission at maximum frequencies in the window of sensitivity of the established bows. So here is a plot showing the region that is still allowed. So those of very low mass are evaporated, and the one here are partly excluded by gravitational lensing, but they can still fill up a fraction of the dark matter component. And what you see here is an example of last milliseconds of life of an spiral with a Saturn mass that would give a emission frequency to around 2 megahertz. As it has been discussed, the frequency is changing very rapidly, so the excitation or decoupling to resonant mass device would be decreased. But the history of this binary is much longer. Essentially, if you look at this plot that is taken from this paper, in the range of sensitivity, the bows can see, well, depending on the mass of the spirals, the last day or the last several seconds of planetary masses, primary black holes binaries. Those that would collapse now, so in the late universe, were formed in the early universe, so they have an history of order 10 gigayears, and so in a region that is not shown in this plot, at lower frequency, they would emit also in where other detectors are sensitive. And as you see, the emission frequency spans several order of magnitudes in the last day of life. correlations in amplitude, time, and frequency can be exploited in gravitational wave detectors designed for broadband or at least multiple frequencies responses. So that is one thing that one should aim at. And that is also actually a key in the detection of chips in the current interferometers. And so what you see here is kind of a standard slide showing the two main classes of detectors, interferometers and resonance mass detectors. So as you see, those have a broadband sensitivity, but a limit in the frequency, around a few kilohertz, while resonance mass detectors that have been established in several years ago have a narrow band sensitivity, and the bars at resonant frequencies of order of 1 kilohertz, and we are now pushing to higher frequencies. So as it was stated, to detect a symphony of the universe, a xylophone would be needed. So you need to expand that to be sensitive to several frequencies. So those two main classes are then coming in many flavors, and here is a list. What I will discuss is these bulk acoustic wave resonators, and which is a resonance mass detector, as I said, and it has been already implemented into an experiment that has reported evidence for rare events of uncertain origin at a 5 megahertz frequency. And you will hear a report later in this session about updates on that measurement. So what is the device? So here is a picture of silicon dioxide, so quartz bulk acoustic wave device, where the device is piezoelectric, so any stress, mechanical stress, would convert into an electric signal. And those are shaped in order to have a high trapping of the vibration modes and little loss, mechanical losses to the supports. And so the sensitivity is coming through a high quality factor. And the difference with respect to the resonant bars is that the transducer is internal to the device, because you directly have a piezoelectricity that provides you the signal. Only the odd overtones, however, are audible, because if you have even overtones, then the integral of the electric field over the crystal gives you a zero potential difference on the two sides, and what you read is essentially the potential difference and then the current induced by that on the two sides. The technology has been established over 70 years ago for precision clock application, as I said, and it is scalable, so you can have many of those. The production capability of those in the industry for precision clock application is of order of 10 to the 6 per year. Okay, so each of those have a response to several frequencies. You can excite 3 family types with different velocities, transverse and longitudinal waves, and multiple overtones. So here is a formula where V is the velocity and D is the thickness. So you can also modify the thickness if you want to tune the frequency. And the plot here shows a few, for one example, a few of these frequencies for the 3 modes are the 3 lines, and this is for the overtones number 3, 5, and 7. Okay, so then the readout concept is described here, which is taken from is a small modification of a seminal proposal that was described by Maxime Goryachev and Mike Tobar in this paper. So you have this resonant cavity plus transducer that is coupled to an amplifier, which is a squid device. So you have a current that is induced through here, and you read the flux with the squid, and then the signal is sampled and digitized, and you log data. And so you have the displacement is converted into the current plus a noise. Then you have an additional noise from the amplifier, and then you have your data to analyze. So the broadband sensitivity is provided by sensing multiple overtones per bow, so per cavity, and also you can build an array of many bows tuned to different frequencies, and that requires a specific R&D on the bows, because essentially for clock applications there are standards, and so you can have 10 to the 6 per year, but all at the same frequency. And so what we are now having as a program in Milan is to build an antenna with several of those bows, potentially tuned at different frequencies to cover a broadband. And so there is an acronym that if you translate into the Milan dialect, means it says Bauscia, and Bausch means a person that actually pretends to be what he is not, like a particle physicist doing gravitational waves. Okay, so here is the sensitivity. This plot is illustrative. It's not precise calculation. So the black band here is MAGE, so this experiment in Australia that is working at a single frequency. Well, now it's updated. It was working at the different frequency when it made this plot. And this one is what you could potentially do if you adapt several of those bows and combine the sensitivity. One has to remember that this is showing an envelope, so it will not be like that. It will be a combination of several lines. But fortunately, some of the signal will span over the different frequency, and you can get the correlations. And you also see here some the sensitivity of other devices, and the lines here shows the maximum amplitude that you would expect from a source within the Milky Way, within the local group, or at 100 megaparsec. And those are scaled from the signal of this event that was observed by LIGO. And okay, and what you see here in the other sketch are the two events that were one of the events that was observed by this antenna, MAGE antenna at the University of Australia with this 5 megahertz signal in coincidence on two devices. And so the antenna that you are trying to build would be complementary to large interferometers because it would cover a different frequency range, and also supplementary to MAGE because having a coincidence measurement with another device would could confirm the origin of the signal. Okay, so then how it works as a gravitational antenna. So here there is some math that is taken from the paper by Maxime and Tobar, and including an erratum that I'm not sure was submitted yet.
It's going to be out any.
Yeah, okay, it was submitted, but it's not yet out. So it comes from, the erratum comes from the integration here that was made from 0 to 2h instead of minus h to h. And so there are some changes in the coupling coefficient that tells you how the device is responsive to a gravitational waves. And it ends up having this factor here that scales as 1 over n to the square. So you're essentially sensitive only to the low overtones. Then you lose the sensitivity, even though the quality factor is actually increasing with the overtone. And the line here shows the sensitivity of a resonant bar. A resonant bar would be the equivalent of a bow without curvature that is used to trap the vibration modes. And the trapping coefficient are made explicit here, so there is this dependence on the curvature. It gives us some improvement in the sensitivity, but it's not order of magnitudes. Okay, then if you want to know, well, then, yeah, the other aspect is what is the noise and the system, and it turns out from measurements that were reported here that the noise is dominated by the thermal noise of the bow itself that is amplified through the quality factor. And while the noise of the amplifier of the downstream readout chain is negligible, so then you can work out the single-sided spectral density from spectral density of force fluctuations in the bow. And this is the expression. And essentially, so what you have here is almost independent of the frequency. There is some mild dependence of the Q factor that improves with the frequency, but it's under a square root. And so the dominant term is coming from this part here, where this psi depends on 1 over n squared, and the frequency is with n. So you have that the max sensitivity is goes well. It's at low overtones, and scale is 1 over n. And then, of course, you improve sensitivity at cold because the noise is the thermal noise is reduced. And so, for translating measurements into a plot, that is what you would get for a set of cavities that were tested in Australia, where you see that you can achieve sensitivity below 10 to the minus 21 per root hertz for low vibration modes, and then it starts degrading, and that is at 20 millikelvin. The current antenna that is in operation is working at 4K, and so you have a bit more noise, and the sensitivity is up here. You will have details on that in the next presentation. So that shows you that if you want to expand in sensitivity and frequency, you need to have devices that are working on the low overtones, but having a fundamental frequency in at a higher frequency. So then here are the samples. So the samples that is used in University of Australia, they have in use two BVA quartz cavities that have a specific low loss design. So they are described here. In addition to the curvature, the vibrating mass is separated from the support because the support is an external frame that is attached, well, to which the device is attached through this annular ring, and the vibrating mass is connected to the ring only through these bridges, and so the mechanical losses are coming only to these bridges, and the performance at room temperature is over 10 to the 6, and at cryogenic temperatures the quality factors improves to better than 10 to the 7 at low overtones and up to 10 to the 9 at very high overtones. The one that we are using in Milan are these off-the-shelf quartz cavities available from one of the vendors that exist. And so this is not exactly optimized for low-loss design, but it's still achieving 10 to the 6 at room temperature. It is here. So the details, the information on that are not many because the vendor is not disclosing information. So we had to broke one to see how it was. So it is there are 4 holders that are directly attached to the quartz, and then there is an electrode that is deposited directly on the quartz, which is not the case here. The electrode is on the support, and that of course implies that there are some losses through the electrodes. So you shouldn't expect this to be as good as the other one, but they are still close. And okay, so those are optimized both for a third overtone, responding to about 5 megahertz, which is the clock standard, and at n equal 1, which would be the one with the largest coupling to the gravitational waves. They have low response, low Q, because the losses, the mechanical losses are too large. And so that is an optimization that would be needed. Then the improvement at low temperature is, well, is coming in the next picture. So let me show, where I'm going. The wrong direction. Sorry. Yeah. I commented there is some improvement. So here is a setup for the characterization. So This is a cryostat, and the samples that we're testing is down here. As you see, there is room for many of those in one of the cryostats, so you can actually build an array. And so we are studying the Q by through the acoustical coupling to the electromagnetic response, and from an impedance analysis. Here is a model, and so you see the resonance and how it matches with the theory. And those are the overtones and frequencies that we observe, and the Q factors that we observe with this off-the-shelf bow. It is optimized for NC = 3, so this C mode for this frequency, but then we see several other frequencies that spans from 5 to 16. Well, actually, there are many more up here, but I've not shown. You lose couplings. And those are all consistent with the expectation, given the velocity of the waves inside the bows. And then, in addition to this, you may see that there are satellites, and those satellites are blown up in this picture here, and those are associated to angular modes. So you may have also different distribution of the wave in the XY plane, and there is a theory that describes that, and all the lines shows that we are actually matching the theory. So the devices are reasonably well understood. So then when you go to low temperature, there is an improvement in the Q, that is shown in this plot that is taken from this paper. And so when the most important loss that you have to avoid is the losses due to the mechanics. You have to have a small coupling to the environment through a good design. But once that is achieved, you have residual losses that can be reduced by going to low temperature. So it's a phonon-phonon dissipation to the acoustic phonon scattering by thermal phonons, and that goes like T to the 6, it's this line here. And then there are two-level system absorption that are attributed to the impurities within the crystal, and that is the other dependencies that you have here that is smaller. So these different curves are for different overtones, and as you see, by increasing the overtone, you would get very high Q factors, but actually the coupling, as I said, is good only at lower overtones, and that is the region we are focusing on. And so here you see a comparison as the low T behavior of the off-the-shelf bows, and you see the same dependence here, then they tend to saturate a bit more than the others, and that is tentatively ascribed to the manufacturing differences. This is not optimized for low losses, but the quality factor that is achieved is comparable to the one that is in the current setup in use at Mage, and so those are sufficient to set up a gravitational wave detector that could supplement the measurements, and the expected sensitivity is sufficient to compare with them, and that is what we are now building. So we expect to be ready by late spring next year. We have dedicated speaks in arriving, but the lead time of vendor is very long for that. So, and while we are keeping on testing bows and thinking to optimize the design, so the next step would be customizing the bows by working on the shape and curvature and thickness to obtain different frequencies, and also minimize the mechanical losses for n = 1, which is where the coupling to the gravitational waves is maximal. So the reference design is this one, but we are thinking on increasing we are studying options to increase the curvature, or may have, instead of a plano-convex design, a double convex design. And so as you see in the plot here, thickness is between 0.5 and 20 millimeters, match the region of interest for the coherent sources. So you would be able to span from of order 100 kilohertz to up to a few 10 megahertz. Then if you want to go up, actually up to the 1 gigahertz, with the low overtones, you will need very thin devices. And so this design with the very thin device floating between supports is probably not optimal. There are options that are associated with the development of the bows for the 5G communications that are working at the gigahertz level, but those need to be studied. So it's microelectronics stuff. We are also considering different material type. Quartz is largely available and that's a very low cost, but producer have their market and they are not very well, they do not welcome us asking for too many modifications. So we need to, well, we have identified a few potential crystal manufacturers, but we're still in discussion. This one has a higher cost, but there is the vendors are available for discussion. And I have here an asterisk because those bars have been in the shape of a bar, so those have been used, for example, with a bar of a length up to 10 centimeter, showing a Q factor of 10 to the 6 at 40 kilohertz. So what it's on this slide here is not just for fun, but there are actually applications that are showing those performance. And so with this, I'm coming to the summary. So this is a summary that was shown by Maxime in a Trieste workshop. And so there was a plan with gray that was said that this is doable or done, and they actually have an antenna that is working. And then there were two red lines, which were harder to achieve, design of dedicated Bose cavities and multi-site detection. So then the new summary here is that the broad range sensitivity requires many Bose of different thicknesses because the sensitivity scales as 1/n, and that is a new information. And the optical sensitivity is n equal 1, so that is what we would like to optimize for. And then there is a plan to develop dedicated Bose in collaboration with UVA and Milan. And in Milano, we are setting up a second detection site. We expect a sensitivity comparable to MAGE. And so actually, the conclusion here is that the xylophone is being designed to detect the high-frequency symphony of the universe. Thank you.
Thank you. Question?
I was wondering if there is any way of designing a heterodyne detection scheme with these detectors where you excite, say, the fundamental mode and the gravitational wave couples to it and moves phonons from the fundamental mode to a higher mode. So in a sense, the goal would be to benefit both from the large coupling of the gravitational wave to the low N modes as well as from the high Q factor of the higher N modes.
Well, I guess it may be possible, but one has to match the frequency difference of the two, and that is of order of...
Yeah, so you'd be sensitive at one particular frequency, but given that the signals that we are looking for, many of them are broadband or at least scanning over frequencies, that may not be such a big limitation. I mean, many other detection concepts have that feature as well. I'm more wondering if this is technically possible, if there can be such a coupling, phonon, graviton, basically.
I don't know the answer.
I think so, but you might need to make a couple mode system. There might be ways to do that, but
it would certainly require a custom-made resonator. You probably
definitely
couldn't take the ones off the shelf. Yeah.
Okay. It's crossed our mind in the past.
Okay, thanks.
Yep.
In one of your first slides, you showed supposed detection of a gravitational wave in two independent detectors. And I was wondering whether it's natural to have glitches, like the ones they look there, at 5 megahertz. Where would that come from, if it's not a gravitational wave?
I believe the presentation by Will Campbell will address that point, because they...
I'll answer that question in 40 minutes.
Yeah.
Yeah. Oh, you mean 15, I think. Yeah. Oh, they were very rare events. They were the only events we saw.
Yeah, so there's a couple of things there. You know it's not like a transient impulse because of how long it takes to decay down corresponds to the high ring down of the quartz, which is order of seconds for the high Q. So you know it comes from the crystal. The most likely possibility is just a charged cosmic particle smashing into the thing and ringing it up. But in the paper where those are published, we discuss multiple possibilities of what it could be.
Any other questions? No, that was great. It's good to have more people working in the field and building bores. It's exciting. So thanks for your talk, Tommaso.
Thank you.